all. This is Structure Definition 101. So we're going to talk about the delightfully complicated resource in the FHIR specification called Structure Definition. And since there's a lot to tell you about, I'm going to stick to the basics. So I want you to know enough to get into Structure Definition and be able to actually read the other documentation we have on it in the FHIR specification. So my name is Ewout Kramer. I work for a company called FHIR from the Netherlands. I also work on the FHIR core team and the lead developer on the .NET API. And Structure Definition is one of the parts of the FHIR specification that I have been working on mostly together with Graham. And it's a foundational resource because we use it to define what's in the FHIR specification. So to give you a little bit of context, Structure Definition is one of the resources we call the conformance resources. So the conformance resources are resources just like patient and observation, but instead of talking about medical data, they talk about the FHIR specification itself. So these resources define what's in the FHIR spec, and in fact, these resources are fed into our publication tool to produce the HTML website, which we then upload to hl7.org/FHIR. So it's the metadata of the FHIR specification, amongst other things. And there's quite a few of these conformance resources. So Structure Definition there is one, but on the REST side of the FHIR interface, there are things like capability statement. That's a resource that can express what your FHIR server can do, which parts of the FHIR spec you're implementing. And that refers to things like operation definition and search parameter that are resources that define which search parameters you support on your REST API, what they're searching on, and so on. So these are all metadata. And all of these can then be referred to from a resource called implementation guide, which, in fact, can produce a human-readable artifact that's published on the FHIR website. And one of the most famous ones is the FHIR specification itself. But, for example, the Argonaut implementation guide also contains most of these conformance resources to specify how Argonaut uses FHIR. That's one example of a set of conformance resources in the implementation guide. So Structure Definition is a resource, and it defines the structure of data, where the other ones are around operation definitions and such. Structure Definition is a very core part of the FHIR spec because it defines what is, for example, inside a patient. Structure Definition says a patient consists of these elements like active and family name, and so on and so on. So first off, Structure Definition itself is a resource, which is a funny thing. That means that any FHIR server, next to having a /patient endpoint where you can go to, can also have a /Structure Definition endpoint. And it's dealt with exactly the same way you would deal with an observation or a patient resource. So it's exchanged with the normal FHIR XML or the FHIR JSON. And so a registry service like registry.fhir.org or Simplifier actually exposes structure definitions on its endpoints. So you can easily get to this metadata of FHIR without any new technology. It's a resource all by itself. And it's defined just like all the other resources in the main resources page on the FHIR specification. And it describes, well, actually it does two things. It describes a definition for the logical core resources like patient and so on, so what's in there. And the definition here is both the structure and additional business rules on them. But it also describes constraints on such structure definitions. I won't go too deep in there, but that's what you do in your profiling. There's been a lot of profiling tutorials already here at DevDays. But basically what you do is you take the base FHIR specification and you say, well, we're not using all the features of patient or observation. We're restricting it to a subset because for my use case, we're just using a subset. And Structure Definition is also used to define that subject, that subset. So it's kind of a contract between the client and the server saying, when you're talking to this endpoint, we're actually using a subset for this use case, a subset of what's in the core spec. And Structure Definition does that as well. So it does two things. One, define the full resource, And B, for each use case, you can create a structure definition that defines a subset of another structure definition. And that's called a profile. And on top of that, you use it to define extensions. And I'm going to show you how that works later on. So where do you use structure definitions? So as I said, it's part of an implementation guide. It's the computer-readable part of an implementation guide. And many times, and the tooling around implementation guides mostly will take a structure definition and make these pretty pictures of a tree with all the elements, data types, cardinalities, and so on. The base for all these pictures in the FHIR specification, whether they look like UML or a tree, the base for all that stuff is structure definition. And once that's loaded into a FHIR server, you can call the $validate operation on the REST endpoint to validate a concrete FHIR instance against such a profile. So create a structure definition, upload it to a FHIR server, and then from that moment on, you could validate instances on that FHIR server using that structure definition by just saying, does this instance indeed agree to all the constraints in that structure definition? And further on, instances have a resource of metadata profile where they can claim conformance to structure definitions. Obviously, servers could verify that, so when there's data coming into a server, they could look up these profile claims and say, hey, are these claims indeed true? In fact, true. If I validate this instance against a structure definition, does it validate? So those are 4 typical uses of structure definition. Structure definition, friends call it SD. It's a long name, so let's I'll use SD from here and there. So where to find, if you wanted to take a look at the structure definitions, just an XML file, where would you look? Let's see. I could just open up a browser and show you, because here we go. If we go to hl7.org/FHIR, that's readable, I hope. Let's pick a resource here. So this is a very familiar page for those familiar with the FHIR spec. And as I promised, within this list, structure definition itself is present as well. So that's here. But not to confuse you, let's just take patient. Huh. Slow Wi-Fi? No. Oh well. I was, no. Okay. That was too optimistic. Do I have an offline copy? Well, anyway. Nah, this usually works. It's just, see? It's just slow. Well. Too bad, but I have it here on my presentation as well. If we would actually have shown patient, and maybe it will later on, you see that neat tree of patient showing all the data elements. And underneath it is a link with the definitions, alternate definitions, XML and JSON. And if you click on XML and JSON there, you would get an XML or a JSON file representing that structure definition. So to confuse you a little bit, structure definition itself, which is a resource, has a link like that too. So you would get a structure definition describing what structure definition looks like. We had a chicken and egg problem there, but we solved it. If you want all of them, you can go to hl7.org, download, and you get all those structure definitions that describe the full FHIR specification. Also, they could publish on simplify.net, registry.fire.org, and as I said, any structure definition endpoint, you could download them. That's how you would get them. And it's interesting to download a few and take a look at what's in them. So what's in structure definition? You're not supposed to really be able to read this, but I'll tell you that structure definition is mostly, so it defines a structure, and on top of that, it has a lot of metadata. So structure definition starts with what kind of thing is this? Who's the author? What's the status? Is this draft? Is this for publication? Is there a copyright? And so on and so on. All kinds of authoring metadata, which is not of real interest to us. The interesting stuff is on the right-hand side. It also has two nodes, one called snapshot and one called differential. And both of them actually are long lists of a data type called element definition. And for each element in a FHIR data type or a FHIR resource, there would be one of these element definitions saying this is patient has active, it has human name, it has such and such and such. And that is all captured in the nodes snapshot and differential. So what is a snapshot and what is a differential? There's two ways to view. So say I'm constraining a patient to define an Argonaut patient. What I could do is repeat all the stuff in patient and then change the things that I had to change for Argonaut, which is maybe cardinality changes, binding changes, and so on and so on. That is one possibility, but we also offer you the possibility to only define differences with the base. So given the patient definition in the FHIR spec, Argonaut only changes these 5, 6, 7, or 8 aspects. And the differential would then have only these 8 differences, while the snapshot would have all of it. So authors of structure definition can choose to either only populate the differential or populate the snapshot and the differential or the snapshot. You could, given the FHIR spec and the differential, you could, of course, regenerate the whole snapshot yourself if you have the differences and the base. But there is a choice there. So this is base patient. So to be clear, the piece of XML I'm showing you here is part of what's inside snapshot for patient in the FHIR spec, so the base patient. What I'm going to do with you now is say, okay, I have a structure definition that is patient. I will show you a little differential of I'm going to change a few things in that base patient, and then I want you to show the net result after merging the two. So that's how you create a new structure definition that constrains the base patient. So let's take a look at the base patient. It has whole lists of elements. So you see here, snapshot, 0 to 1 to star elements of type element definition. And there we go, next. And so here is element, 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 and so on for every single thing that's in patient. Patient.identifier, patient.active, patient.name, and so on. And of course, it defines it element by element. Patient identifier, identified its patient, 0 to star, so it can repeat, and we know the patient identifier field repeats, and it's of type identifier. So look what's happening here. This structure definition for patient actually refers to another type called identifier. The definition of identifier itself, which is one of the data types, is not here inside base patient, because you could just look this up by looking for the structure definition of identifier. And then we have patient.active, and so on and so on. There will be quite a list of these things. So that's base patient structure definition from the FHIR spec. Now let's do a simple new structure definition that constrains this one. I'm going to show you the XML here. You're probably all aware that there are tools like Forge and Trafolia that help you do this in a slightly more user-friendly way. But I'm figuring, since you're following Structure Definition 101 here, we all want to know a little bit deeper what's below those tools. So I'm not going to use any fancy tools here. I'm going to show you the XML to learn what's inside Structure Definition. And once you know this, you probably prefer to use the more user-friendly tools, but at least you know the insides of Structure Definition a little bit. So I am going to define a new structure definition, which is on the screen here. And this structure definition is identified by this URL. Example.org, FHIR structure definition, patient, and it says IK, but it should be EK, my name, my initials. So this is my new structure definition based on, and look, here is an element called base definition, based on HL7.org/FHIR structure definition/patient. That's the normal core patient. These things, by the way, are called canonical URLs, and they uniquely identify worldwide a structure definition. So if you're creating a new structure definition, you'll be making up a completely unique canonical URL. And that's how one structure definition or an implementation guide refers to another structure definition. So there's some metadata here. It's based on FHIR 3. I'm defining a structure definition resource and so on. That's here in the metadata. And I'm constraining patient. Now, instead of a snapshot, which would have never fit here on this slide, the only thing I'm showing you here is the differential, because I'm changing, compared to base, only one thing, and that's patient.identifier.use. So that's the only thing that's in here. It's just the change I am making. So but this structure definition is defining different from the base patient. Patient.identifier.use. And the only change I'm making is setting its max to 0, which effectively says if an instance is valid according to this structure definition, patient.identifier cannot use an element called use, because I have set the maximum cardinality to 0. So you're effectively crossing out that element. Now, there's a subtlety here. When I showed you the base definition for patient, I told you, and we'll take a look, that there is just patient.identifier of type identifier. And what I've done here, I've walked into the identifier type to say something not specifically about identifier, but to say something about something that's inside identifier. You know, with the same thing, I could have said patient.identifier max 0, and then this patient would, you know, the only valid patient would be patient without any identifier. But I thought I'd spice it up a little bit, and because that's the obvious case, and walk into the identifier type and say something about use inside the identifier type. Now, when I merge these two, when I'm creating a snapshot of these two, it starts to look like this. Well, at first, this guy here is definitely under 1K. The snapshot is 490K. Why? Because it includes all elements from patient, plus the base class of patient, which is domain resource, which has things like meta and implicit rules and language, plus resource, and so on and so on. But look at what happened to patient.identifier. Patient.active is somewhere down here still, but now we have patient.identifier here. And we have identifier.use, patient.identifier.use here. So you can see that certainly now this structure definition not only includes patient.identifier, but it has taken on board the full definition of the identifier to be able to say, hey, look, patient.identifier.use now has a max of 0. But it also still includes the minimum value, which was unchanged, the type, which is unchanged, and so on and so on. So that's why the snapshot is 490Ks. But it does contain everything you need to validate an instance against my new structure definition that I'm defining here. And by the way, as you can see, these elements are not nested. It's a flat list. You are using the path here with the dots to specify the hierarchy within a structure. Yeah?
Since this is 101, I assume I don't have a stupid question. So can I change the identifier complex data type just at the data type level and not have to do it within each?
Good question. Yeah, so I'll repeat the question. What I'm doing here is saying I'm using patient as a base, walk in identifier, and change something in identifier. Could I not have changed identifier itself first? That is absolutely possible, and it's a different use case. And there is a very good use case why you would do that. Say that you have your own identifier, say Argonaut identifier or my name identifier, and if I define identifier to say cross out use, and I put that in a separate structure definition, I could reuse that definition wherever I wanted to refer to that kind of identifier. Whereas if I do it this way, this kind of like a one-off. In this patient only, identifier cannot have use. So many times you will do it that way, and then say, by the way, this patient's identifier is constrained by, oh, I didn't put it in here. It's in another structure definition, and that does exactly what you were asking for. You can certainly do that, but both are possible.
But if you changed identifiers, it would be for everything.
Yes. No, well, no, you're not changing the identifier from the base spec. You're creating a new structure definition called my identifier. So, you know, right? Because you can never.
But then you have to substitute that in.
And then you have to, well, and then you define, let's say, something my patient, and then you'll say my patient uses my identifier. That's how you would normally do that.
But once you change it, it's applicable to any request coming in for the validation or validation to this structure.
Yeah, so if your server validates any incoming instance against this, then from that moment on, all the instances have to agree with that. But that's not normally done that way because your server accepts all kinds of use cases for patients, so not specifically only one structure definition.
This is similar to the, not similar to same as the XSD, and it's just defining XSD.
It's absolutely similar to an XSD. Yeah. So the XSDs, cardinalities, and so on. Structure definition, though, in the FHIR, we have a little bit more things like terminology bindings and other kinds of constraints. Well, in fact, it's interesting that this next slide shows exactly what would happen if you would create your own identifier. So here what I've done is I have created a differential that actually says, hold on, I am constraining the core patient, so the structure definition might be called, as I said, my patient. And what I'm doing here, I'm not changing a lot on patient.identifier, but I'm saying this is, you know, our familiar old identifier, but it is profiled by another structure definition that I have defined. See, so that's exactly how you would do that. First, you go out and author a structure definition called identifier NL in this case, and then in this patient refer to it and then says, look for further constraints inside here. I'm not going to write them out in here. To spice this example up a little bit, I have not only said that, but I've also included an additional constraint on identifier use. So maybe this structure definition here, identifier NL, says there should be at most 4 identifiers. Or no, identifier must have the Dutch identifier type, whatever. And then here, additionally, I'm even saying, well, but you cannot use. So here I'm actually combining the two things that we have been discussing, both referring to some other definitions and my own. So the question is, of course, is if we turn this into a snapshot, what would be the net effect of combining both things? I think I have a schematic presentation here for that. So here is the structure definition patient, which has patient.identifier. And I have created a new structure definition called patient EK, my initials, my patient. It says 2 things. Both, I'm changing patient.identifier to not the core identifier definition, but the Dutch identifier definition. And I'm adding constraints on identifier.use. And of course, who knows what identifier NL is doing? Maybe it also has constraints on use and identifier.system. Yeah. Yeah.
Based on your extensive use of doing these, what has been your best practice for naming these? Putting the EK in front so that all the pairs are together? Putting it behind there so that all the patients are together when they show up? You know, I'm just kind of thinking in terms of process when I'm working with sorts better.
Sorry. Yeah. Yeah, I will. Yeah. So the question is, based on your experience with doing these, what is the naming scheme? What's the the best naming scheme? I think what I've seen most is doing it this way with kind of suffixes. But I can put you into contact with people who have done this for multiple nations to see if they have found things across countries that are similar. So I would be glad to point you to them. Yeah. So the net effect of doing all this is take patient, add the constraints from identifier.nl, and when you've done that, add this one. So it will have these constraints and then overridden with this, and then combined into the snapshot. So since snapshots are so big, why would you do this in the first place? Why not just send differentials around? They're lightweight, they contain everything you need. Well, there's a good reason for that. Actually, initially, in the FHIR DSTU1, we had only snapshots. And that's because for a human being, it's pretty cool to see only the differences. But if you're a tool, you really need to do validation. You need all the information anyway. And if you would have only have structure definitions with differentials, you would every single time again have to generate a snapshot before you could do that. So all these kind of, because structure definition can be constrained by other structure definitions, which can be constrained by other structure definitions, and so on. So you'll have this whole tree of generating snapshots. And all of these might point to websites where you can find these structure definitions, where you can find the value sets. You have to include all that stuff to be able to generate a full snapshot. All these sources might not be accessible at times. So a lot of tools, like Forge and many others, what they do is, once you save your structure definition to disk in an XML or JSON file, they will run that at authoring time. So instead of at runtime, any server has to do all that, at authoring time, they will compose a snapshot for you and include it in your XML file. So then everything is packed up in your app, and once you start using the structure definition, all the information is inside as a contained unit. Oh yeah. So the question, I think what the question is, why wouldn't I download the stuff from the FHIR spec and just change it there? Yeah, well, the base. It's not, I mean, you're using the same canonical URL that's supposed to be unique for something that's entirely different, and it's not yours, right? So I think locally that will work, but once you're sending data around, that would confuse everyone because it would say, I'm compliant to patient, and it's not. Yeah, you're patient, but not the one in the core spec. So if you're using it locally, it might probably work, but as you exchange data with others. So the question is, when you generate a snapshot, would you keep the differential? And all the tools do that, yeah, because that would allow you to regenerate, as you said, regenerate a snapshot. And in fact, that's what you do quite a lot initially, because we kept on finding bugs in our snapshotting algorithms. And then you're really happy that you still had the differential because you could rerun it without losing the intention of the author, because that's captured in the differential. All right. So that's snapshots, that's differentials and snapshots. All of they are lists of a data type called element definition. And so element definition is the core of structure definition, because structure definition is just metadata plus lists of element definitions. And element definition is a data type. And the data type has the most important part. It has a lot of elements. But the most important parts are path, which is the dotted notations with which you point to, where I'm talking about patient.active here. There's a short in the definitions, which is human readable text about what that element does. Min and max, the cardinality, specifying the cardinality. So far, min and max is in XSDs too, for example. Then there is fixed and pattern, which says, I'm going to fix the value of this element to a fixed value. So you could actually constrain, for example, patient to say, my patient, all of them are females, by fixing the value of patient.gender to a fixed value. Type ref, which is what you use to, for example, say this identifier is not a base identifier, but identifier NL, so we'll see a lot more of that. Binding, which you use to change the binding and to localize the bindings. on an element. So like marital status in a patient. Probably for other use cases, you're going to change that value set, and you can do it with this. And finally, there's lots of invariants formulated in FHIR. I had a tutorial on FHIR yesterday. That's where these things would go. So I'm going to show you a few more details about how, the obvious things like patient.active, you now know what that looks like, and patient.identifier, what that looks like in the structure definitions. There are a few things that are less obvious, and I want to point them out, how they are represented in structure definition. So you all know this is from observation. Observation.value actually has multiple possibilities. Quantity, codable concept, string, and so on, a whole list. So that's one thing that we have, a feature in the FHIR data model. And on the other hand, you have something comparable. That is where you have a data element that references another resource. And that most of the time it looks like this. Reference of type, practitioner, patient, related patient. There is a list of types of resource that it can point to. Both of these things can be restricted in a structure definition. I'm going to show you how you do that. So first off, let's take a look at this. Within element definition, so this is observation.value x, that stuff is stored in the type element. So in the base definition of observation.value, it just lists all the allowed types, quantity, codable concept, string, range, and so on, one-on-one, just as you saw in the definition. Now, if you're saying, well, hold on, but my observation is just about quantities. In your structure definition that you're basing on observation, you could leave out all these ones and just keep quantity. Basically saying, any instance that's valid to my structure definition can only have quantities, because we're talking about, say, blood pressure. So you could also say, a structure definition for blood pressure will most of the time erase all these types and just allow quantity for observation.value. Question?
Does the bracket in X, does that have any special meaning, or is that just convention that's called with your own?
Yeah. So do these brackets here mean anything? Well, these are just convention. It's kind of like the value, quantity, value. You see the place where the name of the type appears in the instance. That's also where the X is. So that's how it came about. And you'll only see this in structure definition in the path. OK. Just as I showed with patient.identifier, you can now limit observation.value to a subset, as I said. And additionally, you can still do what I said and say, this is not just a quantity, this is a weight quantity. This is not just a ratio, this is a weight ratio, just as I showed with identifier. So you can combine these two things. Looking at these references, that's the other feature that I showed in the red box. Let's take a look at observation.subject. Observation.subject can be a device, a location, a patient, and so on. And this is done by actually repeating the type node in element definition and saying observation.subject is a reference. It's a reference, it's a reference. But there is another element here called target profile that says, what's the profile of the thing I'm pointing to? So here you're not placing any constraints on this thing itself, but you're placing constraints on what observation.subject is referencing to. Basically saying, yeah, you can still reference any kind of base device, any kind of base location, but one of the references for subject, I'm changing it to be not just patient from core, but the Dutch patient as I have defined it. So this is how, once you've defined your structure definition on patient, you could include it here in a reference. Sure. Yeah.
But you want to just reference like the name of the subject because you're not doing devices or anything like that.
Okay.
Can you change that to just be a string?
So that's an interesting question. I'll repeat it. So it's your question, if I understand it correctly, is if you're not supporting yet in your system some of these, but you still want to say, well, I don't have the reference, but it's still a device. Look somewhere else. Actually, the FHIR reference type has support for that. And I think, one slide on, I have the definition for reference here. It's a little bit small, but it has reference, identifier, and display. So here in display, you could say, I don't have a reference, but it is a patient called Emily Watson, for example. You could definitely do that. And that brings us to an interesting, actually, you're offering a perfect use case for something that I wanted to show you here in the form of a quiz, is now you know what I've told you so far. What would happen if I would say observation.subject is a reference, and that reference points to a patient NL, but it's also profiled? What does this combination actually mean? We've seen profile saying I want to change identifier to an identifier that's profiled by the structure definition. I've shown you target profile to show if this is a reference. The thing I'm referencing is a patient NL. What does the combination of these two things do? Elliot.
That is a reference that has to have a display image and can only point to a Dutch patient.
Right. So what Elliot is saying is this target profile here is touching on what I can point to, but this profile here is actually saying something about the actual reference in observation.subject. And so that is, here is a reference data type. With this profile here, you could constrain what's inside the reference data type that you use to specify the reference. And that's quite interesting because that would satisfy your use case. You could, for example, say, well, this is a reference to patient NL, but you know what? The actual reference within reference, we're not using it because we don't have it. And additionally, reference.display, I changed it from optional to required because you need to fill the display saying it points to something, but I don't have it. So please specify a string to say what's inside. And you could use this combination to actually enforce that in a structure definition. Now, it doesn't matter. That's why I put this in a quiz. If you don't get this the first time, this is slightly advanced, but it shows you that you can profile both a reference. So this only works for references, right? Target profile is only of interest for reference. Okay. So just to give you a quick summary here of what we've been doing, I have created a structure definition called patient EK with lists of element definitions that points using its element-based definition to patient. So I'm basing this on patient. Inside these element definitions, I have lists of element definitions constraining stuff, and some of them might point to external profiles like weight quantity. So structure definitions that I want to, that for example, constrain identifier or quantity. And it can point to target profiles if I'm constraining a reference and I want to say something about the reference. And finally, element definitions have an element called binding.valueSet that point to another conformance resource that's a value set. That's a summary of all the references of how you compose a structure definition from other structure definitions. And all of these use this canonical URL. That URL that was there on top of my structure definition that needs to be unique, that you need to figure out once you start authoring structure definitions. Because that's how these things refer to each other. And finally, I want to tell you something about defining extensions. So far, we've been concentrating on saying, I want to put constraints on the base patient. But what you can also do with structure definition is define an extension. And there's actually, defining an extension is a pretty smart, a pretty clever trick that we invented to not have to invent something new. In fact, what you're doing when defining an extension is creating a structure definition constraining the data type extension from the FHIR specification. So in the FHIR specification, the data type extension looks like a URL and value X. That's what the extensions look like in an instance. And if you want to define an extension, say hair color, what you're doing is saying, here's a structure definition with the canonical URL, something hair color, and then constrain extensions by constraining its URL to a fixed value, that is my canonical URL, and then saying, oh, by the way, value X, hair color, is a codable concept. And that codable concept is bound to such and such a value set. So you define something new, a new extension that only exists in your use case by putting a constraint on the base FHIR data type called extension. So in this case, I have here a differential in the structure definition. So what am I doing? I'm constraining extension. Extension itself doesn't have nested extensions in this case. And in fact, you probably have seen complex extensions, and then they probably would. I'm constraining extension.url to a fixed URI, example.org/FHIR/StructureDefinition, my extension, which is exactly the same as the canonical URL for this whole thing. And then I'm moving down to extension.valueX, saying it's mandatory and it's of type Boolean. What I've effectively done is that any extension that conforms to this has this fixed URI and needs to be a Boolean. And if you encounter this in an instance, you know that the URI will look like this. And if you want to validate it, this canonical URL would point to this structure definition. So it's quite a clever trick to define extensions without having to invent yet another resource called, not structure definition, but extension definition. Basically, extension definition is a structure definition with constraints on extension. And that's all I wanted to tell you about structure definition today. There's much more to tell, but are there any additional questions? So when would you do, the question is, when would you do a structure definition, a profile on a resource, and when would you do an extension? Well, a structure definition, if you profile a resource, you actually can only limit it. So you can take away stuff. But extensions are things you add to so if patient has, if you're adding stuff, you're creating extensions in FHIR. Profiles only restrict, yes. And extensions only add, yeah.
And then, okay, suppose that you wrote an extension, but you had different use cases, and you wanted to restrict the exception or different use cases. You then profile an extension.
Yes, you could. That's an advanced use case, yeah. Yeah, so I'll repeat that question because that's the kind of stuff I leave out of in 101. Say I define an extension, and I'm reusing that extension in different profiles, in different use cases. Could I say, if this extension is used within this use case, I want to put extra constraints on the extension? Yes, you could. So you could say, if this extension is used within a patient, I'm using it in a different way than when I'm using this extension in a practitioner, for example. And you could actually do that using structure definition. Yeah, one more question. Can structure definitions introduce constraints that make it incompatible with the base? No. So the tooling should always check for that, because otherwise it's incompatible. That's the new group, so I think we should quit.